Hello, I'm Jung Gi-jang. Today I will introduce our paper Tucker, a fast and memory efficient Tucker decomposition for dense tensors. This is a joint work with Professor Kang. It is today's online. Various real-world data are represented as dense tensors. For example, sensor data are collected from several locations over seconds. Air quality and video data are also represented as dense tensors. Tucker decomposition is a fundamental tool to analyze dense tensors. It learns core tensor and low-rank latent factor matrices representing each dimension from a given tensor. Tucker decomposition is widely used in various applications, including dimensionality reduction, missing value prediction, and clustering. Alternating least square is the most widely used method for Tucker decomposition. ALS approach iteratively updates a factor matrix of a dimension while fixing all factor matrices of other dimensions. ALS requires a high computational cost and space cost for computation between an input tensor and factor matrices. Now I'm going to explain the former problem definition of our paper. Given an another dense tensor X and core tensor size, we find the factor matrices and core tensor. Existing ALS-based methods do not provide one or more of the desired properties for dense tensor decompositions: fast running time, efficient memory usage, and accuracy. Before explaining our proposed method, I introduce challenges of our problem. The first challenge is how can you approximate an input tensor with low computational cost and error before iteration step? The second challenge is how can you efficiently update factor matrices and cotensor using an approximated tensor? Let's move on to the proposed method. We propose Tucker, which is a fast and memory efficient Tucker decomposition for dense tensors. Tucker composes of three phases: approximation, initialization, and iteration phases. Approximation phase efficiently compresses a given tensor. Initialization and iteration phases efficiently initialize and update vector matrices and cotensor by only using compressed data. There is an example of how Tucker deals with third-order tensor. First, Tucker slices the given tensor along the mode having the smallest dimensionality and performs randomized SVD of sliced matrices. Then Tucker initializes vector matrices using the SVD results of sliced matrices and iteratively updates vector matrices and obtain core tensor using the SVD results. Let me explain approximation phase in more details. First, we extract the sliced matrices of size I1 times I2 by slicing a given tensor. And then we perform randomized SVD of each sliced matrix. Compressing slice by slice provides two benefits. The first one is Tucker approximates the given tensor data with low errors by exploiting a low dimensional structure of sliced matrices. The second one is that Tucker approximates the given tensor data with better efficiency by avoiding tensor operations such as M-mode product. Before the iteration phase, Tucker initialized vector matrices using the SVD results of sliced matrices based on ST HOSVD. By avoiding the reconstruction from SVD results of the sliced matrices, Tucker efficiently initialized the vector matrices, and this phase helped reduce the number of iterations. Let me explain initialization phase in more details. To initialize the first vector matrix, carefully decouple US, U sigma, and V, compute SVD of a concatenate matrix of U sigma, and initialize the first vector matrix as left singular vectors of the result. For the second vector matrix, Tucker computes matrix multiplication between the first vector matrix and left singular vector matrices of the SVD results. Then Tucker constructs intermediate data Y and initialize the second vector matrix as left singular vectors of mode 2 matrixization of Y. The time complexity of the above procedure is lower than that of naive computation between an input tensor and the first vector matrix. For mode n, initialize a vector matrix an as left singular vectors of this term. After initialization, Tucker iteratively updates vector matrices and obtain the co-tensor using the SVD results of sliced matrices. For the nth mode vector matrix, perform n-mode products between the SVD results and vector matrices except for the n-mode vector matrix. By using the SVD results of sliced matrices instead of an input tensor, the iteration phase of Tucker yields faster computation per iteration while converging within a small number of iterations. Now I explain the iteration phase in more details. In the iteration phase, Tucker carefully computes n-mode products for the first and second vector matrices. For example, Tucker first computes matrix multiplications between the first vector matrix and the left singular matrices of the SVD results. After that, construct intermediate data Y by computing matrix multiplications. The time complexity of the above procedure is lower than that of naive computation between an input tensor and the first vector matrix and the second vector matrix. Tucker updates n-mode vector matrix as left singular vectors of this term after computing Y. For the co-tensor, Tucker computes this term using Y. Let's move on to the experiments. We aim to answer the following questions from experiments. The first question is, what are the trade-offs between running time and error by Tucker compared to other baselines? The second question is that how quickly does Tucker update vector matrices compared to other methods? The last question is how much memory space does Tucker require for initializing and updating vector matrices? Our experimental settings are follows. We used 4 real-world tensors: BrainQ, BOTS, air quality, HSI datasets. We compare our method with 5 ALS-based competitors: Tucker ALS, MAU, Tucker TS, Tucker TTM-TS, and RTD. The first experimental result is about time and reconstruction error. Tucker is up to about 38 times faster than competitors while having similar error. Let's check the efficiency of the iteration phase. In the iteration phase, Tucker is the only method providing fast computation per iteration while converging within a small number of iterations. For the space cost, Tucker requires up to about 17 times smaller space than competitors. I conclude this presentation. We proposed Dtucker, which is a fast and memory-efficient tucker decomposition to deal with dense tensors. Dtucker has 3 phases for efficient tucker decomposition. Dtucker achieves better performance than state-of-the-art ALS-based tucker decomposition methods. Thank you.